Gonna jump right into this problem. We've got a tension force there, 80 newtons. That's our force of tension at 50 degrees. We're obviously gonna have our force of gravity. All right, we're gonna have a friction force. We don't know if this thing's moving yet. And then the last one here we have that we haven't had a lot of is the normal force. So there's 4 forces acting. So the weight of the box, that's just Fg. Fg equals mg, so 15 kilograms times about 10 newtons per kilogram. It's about 150 newtons. So that would be negative 150, force of gravity. Magnitude of the normal force acting on the box. All right. So we got to break this tension force into x and y components, right? Because what we're going to see is the y component of the tension the y component of the tension and the normal force have to add together to equal 150 newtons. So Fty plus the normal force have to equal the magnitude of the force of gravity. All right, so Fty would be 80 newtons times the sine of 50 degrees plus Fn equals 150 newtons. Now, this is the magnitudes of these, right? The absolute values. Or you could write them all adding up to 0, where 150 is negative. So, do the math here quick. 80 times the sine of 15, or 50. 80 times the sine of 50 is 61. So 61 plus Fn has to equal 150. Fn would have to be 150 newtons minus 61 newtons. That's 89 newtons. All right, 89 newtons of the normal force only has to be, right? So that would be 89, that would be 61. They add together to equal the 150 pulling down. Is the 80 Newton force at an angle of 50 degrees enough to get the wooden block moving? Justify your answer quantitatively. All right, so what we're gonna have here is we wanna see, is Ftx greater than the force of friction static max, right? So let's find the x component of the pulling force first. So 80 newtons times the cos of 50 degrees. Cos of 50. That gives us 51 newtons. And then let's figure out force of static friction max. So that would be mu times Fn. So that would be, we're looking at wood on wood here. So I gotta find the reference table quick. Awkward pause in the video. I don't have these memorized. So wood on wood static is 0.42. So 0.42 times the normal force we already calculated, which was 89 newtons. 0.42 times 89 is 37 newtons. So, is 51 newtons greater than 37 newtons? Yes. So, the force is big enough to break the box free. Okay, it is big enough to break the box free. 0.42 times 89 is 37. The pulling force is 51. Therefore, the pulling force is bigger than the force of friction. It's gonna get it moving. All right, next one here quick. We got a 35 kilogram block, two ropes. Okay, two ropes. There's one, there's the other. I'll call it FT1 and FT2. We've got a force of gravity going down. All right, this is 65 degrees. Okay, determine the magnitude of the force applied by each rope. So we gotta find FT2 and FT1. Well, FT2 has to equal FT1x, right? So if I do that, should use a different colored pen. That would have been a nice thing. FG, FT1y has to equal force of gravity, okay, which is mg, or 350 newtons. All right. You probably would want to show this calculation, so I guess I should show it. That would be 35 kilograms times 10 newtons per kilogram. That's where that came from. All right, so ultimately now we're gonna have to do a couple steps here. So let's get, we know FT1y now, the vertical side. So I'll put a little triangle over here. Right, this is 65 degrees. This is 350 newtons. This will be the x component. This will be FT. So let's find the force of, let's find, I don't know, force of tension first. So FT itself, FT1, that is. So we've got opposite and hypotenuse, that's sine. So sine of 65 equals opposite, 350 newtons, over FT1. FT1 equals 350 newtons divided by the sine of 65 degrees. Okay, so $390 newtons. 390 newtons. Great. All right. Now we got to get FT1x. Okay, the x component of the tension here. So we could do anything at this point. We could use tangent. So tan of 65 equals opposite over adjacent. So 350 divided by FT1x. FT1x equals 350 divided by tan 65 degrees. It's a lot of steps. I probably would break this down into more steps for you on a quiz, but test I might give it to you like this. Make it worth a lot of points. 163 newtons. So FT1x is 163 newtons. Therefore, that's what FT2 is. The magnitude of FT2. So when it says magnitude, make sure you don't put a sign on it. All right, it's just got to be the value of the force. Clearly, FT2 is positive, FT1x would be negative. We didn't factor that in here. FT1 is neither positive or negative. It's at an angle of 65 degrees above the negative x-axis. All right, final one here. So this one we talked about pretty quickly in class, I suppose. FG is still straight down. That's the angle of the ramp there, 25 degrees. That goes right in there, always between the y-axis. If you draw it here first, it kind of can help you figure this out a little bit better. You know, just kind of sketch the forces on this one first, just to kind of get them right. So that angle is the same as this angle. Those are the same. So 25 degrees. Fn is here. Force of friction is here. So in this reference frame, right, the force of gravity has a, in this reference coordinate system, not frame, sorry. Fg has an x component and Fg has a y component. The normal force has to be equal to Fgy. All right, so that's going to be 200 newtons times the cos of 25. So 200 newtons times cos of 25. See, adjacent side here, because this is your angle. Your triangle, right? Your triangle is this triangle. So cos of 25, 200 newtons times the cos of 25. It's 181, I just did that. 180, we'll say, 2 sig figs is plenty. And then the force of friction has to be equal to the magnitude of the x component of gravity trying to pull it down the ramp, because it's going to hold that in place. So 200 newtons times the sine of 25. 200 sine of 25 equals 85. All right, so that component's 85. You don't need to go back and put numbers on all this. Make sure if you draw components that you make them dashed arrows. That's important. So inclined plane is an important thing to have a concept of, especially if you take physics at the next level. So those are static force questions. These are as hard as they're going to get. Probably like some of the hardest problems of all year. I'll get these scanned and posted very soon. Before tomorrow. Well, probably tomorrow, because I have some kids still turning it in.